Okay, we're going to continue our discussion about light, and in particular, this lecture is on spectroscopy. But what we want to know is how much can we learn about light, so that we can use light to learn about other things, in particular the universe. Through spectroscopy, in particular of a star, we can find the temperature. We talked about that last time. That through a black body radiation, if we plot the intensity versus frequency, we can get this skewed curve, and the peak of that curve tells us something about the temperature of that object by Wien's law. So we determined that last time. This time we're also going to discuss how we can get the composition of a star or an object out in space based on spectroscopy. And the motion of the star, whether or not it's moving towards us or away from us and how fast it's moving. We can get that kind of information as well from the light that reaches us. Last time we talked about how the visible part of the spectrum is just a small fragment of the whole electromagnetic spectrum, where we can gain information from all the frequencies, all the waves possible in the electromagnetic spectrum. Well, we can even get more information by using the fact that light sometimes acts like a particle, and based on that information we can figure out composition of the stars and other things. How does this work? Well, slightly more than 100 years ago, Max Planck discovered that the energy of an oscillator was found in discrete quantities. He defined this as saying that the energy was quantized with the frequency. What does this mean? Well, he came up with a constant, now called Planck's constant, and basically said that based on the frequency, the energy was a multiple of that frequency, and a definite multiple based on this constant. So as the frequency went up, so did the energy. And with this idea that it was discrete, that it was in definite quantities, definite multiples of some smallest quantity amount, the energy levels are more like somebody walking up a stairs here, where you go up discrete amounts and increasing your energy, as opposed to, say, going up a ramp where everything is continuous. So that the energy of this oscillator was more in the former situation, where your energy went by these discrete jumps and not in a continuous manner. Well, Albert Einstein extended this theory to electromagnetic radiation, light as we know it, saying that maybe light had this kind of property as well, of discrete jumps in energy. In other words, light would have a dual nature. It sometimes acts like a wave, and it sometimes acts like a particle, a photon, where it's just a discrete bundle of energy. And in actuality, if you were to try to run an experiment to look for, say, its wave-like properties or its particle-like properties, you would find those properties, but it depends on what you're looking for or how you've designed your experiment. If you're looking for wave-like properties, you'll find wave-like properties for light. If you're looking for particle properties, you'll find particle properties for light. You won't find them both at the same time. So you find one or the other, they're there, but in the dual nature of light, you get what you look for. It has both natures. In the particle nature, we then say that the energy is some discrete amount of energy, some multiple of the frequency of the light, this multiple again being Planck's constant. Here's a continuous spectrum of light showing all the colors of the rainbow in the visible spectrum. the wavelength going from a higher value, a shorter wavelength to a longer wavelength, shorter wavelength being in the violet region, longer wavelength being in the red region of the visible spectrum. As we know from last time, that the frequency times the wavelength is a constant. It's the speed of light. So as the wavelength changes, the frequency must inversely change. So as we go from short wavelength to long wavelength, the frequency will go from a lesser frequency to a greater frequency. And since the energy goes with the frequency, the energy will do the same. So we'll go from a low to a high. Hence, if we were in the violet range of the visible spectrum, we are dealing with the higher energy light in the visible spectrum. And if we were in the red region of the spectrum, we'd be dealing with the lower energy light in the visible spectrum. If we go beyond the visible spectrum, where we can't see, humanly we can't see, in other words, if we went above the violet region, we would find ourselves in the ultraviolet region of the electromagnetic spectrum. More energy than what is in the visible spectrum, but you can't see it. You'd be exposing yourself to UV, which is higher energy. And if you went below the red part of the spectrum, you'd be going to lower energy. You'd find yourself in the infrared, infra meaning below, and hence you'd be looking at heat energy. Some animals can see in this range. We can't. But it's lower energy than in the red region of the visible spectrum. Well, there's three types of spectra that we can produce using what is called Kirchhoff's spectral laws. And Kirchhoff's spectral law number 1, if we take a hot wire and we heat it up and we get the full continuous spectrum from this wire, this light, we might set up something like this. We have an electric arc white light source putting out white light in general. We run it through a slit in order to make the light more coherent on itself, so it's within phase. Then we run that light between a prism or through a prism so that it separates the frequencies of that white light into all the colors of the rainbow. And hence we see a continuous spectrum, red to violet, in the visible spectrum. Basically, we're looking at all the frequencies and wavelengths possible in the visible spectrum. Kirchhoff's spectral law number 2 might be obtained by exciting a gas and letting the gas be the source of light. In this case, let's take a hydrogen gas and we'll heat it up and excite it, let it gain energy, and let it emit light, its characteristic light, and see what happens. We run that through a slit to make it coherent, run it through a prism to separate it, and we get an interesting result. We only see specific frequencies of light corresponding to this configuration that we've set up. The hydrogen is only put out specific frequencies of light. Why? We don't see all the other frequencies that we saw with a continuous white light source. Now we only see specific frequencies. And the question is, why? The answer is soon to come. But this is interesting. Suppose we look at Kirchhoff's spectral law number 3. We're going to disperse white light through a cooler gas and see what we get as a result of this. Start with an electric white light source, run it through a slit to make it coherent. This time we're going to run this white light through a cool hydrogen gas, and after it's gone through the gas, then we run it through the prism and we find an interesting result. We see all the colors of the rainbow in the visible spectrum, but now it's missing those same frequencies that we saw in the spectral law number 2. It's devoid of those frequencies in this total spectrum. The question is why? So what is it about this configuration that has caused this? If you take this cool hydrogen gas away, then you would get the full spectrum red to violet of the visible spectrum here. So something's happening with this gas. Well, the answer is, at least for this Kirchhoff's law number 3, is that you start with a white light source with all the frequencies possible. When you run it through the cool hydrogen gas, the hydrogen gas somehow absorbs those specific frequencies that we saw, and those are now taken out of that continuous spectrum, and so what you end up with is the continuous spectrum without those frequencies. A similar idea is if you look at the sun, this is what you see, what is called a line absorption spectrum, a Fraunhofer spectrum from the sun. And here you see all the colors available but missing specific frequencies. And what this tells us about the sun is that there's a source at the center of the sun that is putting out a lot of energy and all frequencies, and somehow between that source and us, specific frequencies are being absorbed, most likely in the outer regions of the sun. In the gaseous part of the sun, there are molecules and atoms that are absorbing specific frequencies, not allowing those frequencies to make it to us, and so we see a line absorption spectrum for the sun. So how does this work? Well, if you look at a basic atom, and we'll look at the simplest atom here with the hydrogen atom with its simple proton at the nucleus and electron traveling around this nucleus. And we know that this electron is traveling at about 100th the speed of light, so it's traveling extremely fast, 2 million meters per second, and is doing it in a very, very small space, so you really never know where the electron is at any particular time. It's in a cloud somewhere around this nucleus flying around. If this were the ground state, the electron would be flying around like this, but if we excite this atom, we might find it in an excited state where actually the radius of its electron cloud is bigger, and hence it's taking up a larger sphere of space. So the average distance of the electron from the proton increases as we put it into an excited state. Well, if we look at this atom, let's try to model it simply. Let's use the Niels Bohr model. The Niels Bohr model is to model this atom as if it were an electron going around definite energy levels around the nucleus. And actually, this is actually a pretty good model. Even though it's a Bohr model, it's actually pretty interesting to have this electron actually obey certain energy levels around the atom. Here's the atom before. But let's say this electron was in an excited state and actually jumped to a lower ground state, and by doing so it went down a definite amount of energy, a discrete amount of energy. As a result, it might give that energy off, or would give that energy off, in the form of a light bundle, a photon if you will, and that photon would be emitted, and that would be a characteristic frequency and a characteristic energy for just that particular transition from an excited state to the ground state. And you would see that line, that frequency, that color associated with that transition. This would explain what happened in Kirchhoff's law number 2, where we excite the hydrogen gas and then we allow it to de-excite, and it's giving off just the frequencies, just those specific lines that correspond to when it goes from a excited state, a high state, to a lower energy state. Well, the opposite could be true. Let's say you had a cool gas, a cool hydrogen gas, and you bring in light, and most of the light that hits it is not going to do anything because it's just not the right energy to make it move to the next state. But some of those frequencies are just perfect to make the electron move from a lower energy level to a higher energy level. Just perfect energy amount, perfect frequency. And when that happens, if you had a full white light source hitting this gas, then the gas will only absorb those frequencies that make it transition to the higher state. Hence, on the other side of this gas, what you would see was the continuous spectrum missing these particular frequencies that were used in order to excite the gas. And that's what we saw with the absorption spectrum. That's what we see when we look at the sun. Well, these lines that we see, either for emission or absorption for a particular element and particular gas, are the same lines. In other words, the same frequencies correspond to the same transitions within that element, within that atom for that element. So, in essence, these particular family of lines constitute a fingerprint for that particular element. So if we were looking for hydrogen, say, and we're looking in the visible range, we would see these particular lines that we see here, and that would tell us, yeah, there's hydrogen there. So these lines are distinctive to an element. Or here, if we saw this kind of line pattern, we would say, yes, okay, there's helium there. It's distinctive to that particular element. It's noteworthy to say that helium was first observed in the sun's spectrum and then discovered finally on Earth 30 years later. So helium, we knew helium existed, but it was actually discovered to be existing in the sun before it was discovered on Earth. But the point here is that you can look out into the heavens, look at the light that's coming in, and from that light you can determine what the elements are in that light. So if you're looking at a particular star, you could determine if hydrogen was in that star or helium or any other elements were in that star, looking at these fingerprints. In particular, if we were looking in the visible spectrum at the element hydrogen, we would see those lines that we just saw, those particular color lines at the particular frequencies and wavelengths. But the visible spectrum is not the only part of the electromagnetic spectrum where you could have these transitions, these energies corresponding to this fingerprint. In fact, the whole electromagnetic spectrum could be used to find the specific frequencies that correspond to that element and the transitions within that element. In particular, for hydrogen, when we see the lines within the visible range, those are the lines that tend to end up at the n=2 transition, or n=2 level in the hydrogen atom. So it's not even the ground state or the first level. It's called the Balmer series that ends up at n=2 and gives us the visible lines that we see. The Lyman series, which ends at n=1, is actually in the ultraviolet. So if I were measuring these frequencies, I would measure beyond the visible spectrum into the ultraviolet and beyond as well to really nail down what this element was. So you could look out at a star, determine elements, or you could look even at a planet, determine the elements, determine the ratio, and maybe if you're looking at Mars, you would notice that there was, say at the polar ice caps, there was some hydrogen and maybe some oxygen, and you might determine that indeed there was water there, which there is at the polar ice caps of Mars. If you're looking at molecules, these transitions, these atomic transitions, are not the only kinds of energy absorption that can take place. Molecules can have quantized energy levels from vibrations, from excited atoms, or in terms of the molecule, absorption within the vibration as these atoms are vibrating back and forth, or rotations. In particular, if you have a water molecule, there might be energy stored in with rotations. It turns out that for the water molecule, a lot of these extramolecular energy levels are actually in the microwave range. So if you were to excite water with microwaves, you would find that water would absorb a lot of that microwave energy and then redistribute it as heat, and that's why water heats up when you hit it with microwaves. So microwaves excite water molecule levels. This was first discovered by Percy Spencer in 1946. Here's Percy Spencer. And what was happening then, if you recall, World War II ended in 1945. And many historians would agree that one of the top 5 things that allowed us to win that war, the Allies to win that war, was radar. Included in that is things like the atomic bomb and the Jeep and other things. But radar in particular allowed England to defend itself from the Luftwaffe, from the Nazis. So after the war, radar was real important. Radar had just been developed. Of course, it had just first been developed right before the attack on Pearl Harbor. And in fact, the radar engineers saw the attack coming, but they didn't believe it because it was a new technology right then. But it was important to develop this radar even further after the war because its applications were definitely important. So after the war, Percy Spencer was one of the lead engineers in studying radar, and he noticed one day when he walked into a room where they were studying the radar mechanisms, he had with him a Hershey chocolate peanut butter in his pocket, and after being in this room with this radar going on for a while, he noticed after a while that the chocolate had turned to mush. Other engineers had noticed this effect and thought it was curious, but to Percy Spencer it was more than curious. He was trying to figure out what was going on here. He started with a peanut chocolate bar, and now it's turned into a mushy peanut nougat type thing. And thinking about this, he came up with an idea. And you know what that idea was? It was Spencer's Nut Goodie. Yes, he came up with Spencer's Nut Goodie. Chocolate on the outside, peanut goodness on the inside, delicious, made him millions of dollars. And then on the side, he invented the microwave oven. Actually, here's a very interesting story about all this. It's from Reader's Digest in 1958. I'm going to read it real quickly to you. Percy Spencer was the nosiest man I've ever known. One day, a dozen years ago, he was visiting a lab where magnetrons, the power tubes of radar sets, were being tested. Suddenly, he felt a peanut bar start to cook in his pocket. Other scientists had noticed this phenomenon, but Spencer itched to know more about it. He sent a boy out for a package of popcorn. When he held it near a magnetron, popcorn exploded all over the lab. Next morning, he brought in a kettle, cut a hole in its side, and put an uncooked egg in its shell in the pot. Then he moved the magnetron against the hole and turned on the juice. A skeptical engineer peeked over the top of the pot just in time to catch a faceful of cooked egg. The reason, the yolk cooked faster than the outside, causing the egg to burst. I'm wondering if these people were worried about this, because here they are seeing all this stuff getting cooked, and they're in the same general vicinity. Spencer discovered that you could cook with high-frequency radio waves. He got a patent on what is called the radar range, one of the 225 he holds. The new device will cook a sirloin steak in 1 minute, a plump Thanksgiving turkey in a little more than half an hour. Used for some time in restaurants, Pullman diners, and ocean liners, radar ranges are now being produced for the home. And, of course, there's the microwave oven. The thing with the microwave oven is it excites the water molecules, and when the water molecules de-excite, they give it off in the form of lower energy range of heat, and that's what cooks the subject. So whatever you're trying to cook has to have water in it. and basically will cook from the inside out. So it defies all the conventional wisdom of regular cooking using heat or fire or a stove or that sort of thing. Here's something else that was discovered by accident. X-rays were discovered by accident in 1895 by Wilhelm Roentgen. And the very first X-ray was an X-ray of his wife's hand, wedding ring and all. Why his wife's hand? I don't know. I don't know why. Maybe he wanted to save himself to doing science, and so he had his wife put her hand there along with her wedding ring. Curious thing, though, over time, Frau Roentgen's hand X-ray changed. Here's the first X-ray that you see on the left here, and you may visualize the story something like this. It became a really interesting phenomenon to see these X-rays being taken. In fact, one time Wilhelm had his friends over, and they were watching the game, and he called his wife and he said, "Honey, come in, it's halftime now, and the guys would like to see me take another X-ray of your hand." So Frau Roentgen came in and put her hand down, and he knows something. Over time, after about 200 X-rays, the X-ray had kind of degraded a little bit. You couldn't see the ring anymore after 200 X-rays. Wonder why. Something else that involves light is fluorescent or phosphorescent material. In particular, these kind of materials absorb ultraviolet radiation, which you can't see, but they re-emit the radiation at a lower level energy, visible radiation actually, which you can see. So if you expose these kind of materials, either fluorescent or phosphorescent material, to ultraviolet light, it will absorb that light and then re-emit it at lower frequencies and may be within the visible range, so you would see all these fancy colors being re-emitted. The difference between fluorescent and phosphorescent is fluorescent, it happens right away. Phosphorescent, it can absorb it and then re-emit it with some delay. Your basic fluorescent light works on this principle, and in fact the coating on fluorescent light is phosphor. So the idea is that you excite this gas, and then as it de-excites, it emits in nice visible light, and that is your light source. It's actually much more efficient, maybe 6 times more efficient than incandescent lights, because in an incandescent light, you're heating the filament, and it's putting out light, but it's also putting out a lot of heat. And infrared, it's putting out ultraviolet as well, which you're wasting that energy. So in the incandescent light, you're just heating up the filament, losing a lot of energy, and you don't have this problem as much with a fluorescent light because most of your energy is being utilized in the visible range. Here's a comparison of hydrogen spectrum, molecular versus atomic. Atomic is easier structure, so you can see definite frequencies. But in the molecular hydrogen, there's more ways to absorb energy, more ways to have energy levels, either in vibrations or rotations. So that spectrum would be far more complicated. So if you were a spectroscopist and you were looking at light from the universe, you'd have to take this into account that possibly you're looking at molecular versus atomic hydrogen. Here's something else dealing with light, radar. We talked about microwaves in the radar range, but what is radar in particular? Radar is an acronym for radio detecting and ranging. How does it work? Well, let's say you send out a radio wave and you hit an object, and that radio wave comes back, and if you know what the speed of the electromagnetic radiation is, and you know how long it went to get there and come back, you can figure out the total distance it traveled. And if it hit an object to come back, then if you take that total distance it traveled and divide it by 2, then you know how far away that object is. So that's the basic principle of radar, is to put out a signal, have it bounce off an object, and have it come back. And you can determine where that object is. If you want to be stealth to the radar, you could do several things. One thing is you could absorb that energy as it's coming in so it never makes it back to the sender. Or you could have facets that would deflect that radiation so it goes off in different directions and never makes it back to the sender as well. Your main objective is to make sure that that signal never makes it back to the person who sent it out, and then you would be invisible to that radar. The Doppler effect is a particular effect that can be used using radar. Here's some intuition to the Doppler effect. If you had a source and an observer, if the relative distance between the source and observer somehow decreases through their movement, then the observed frequency will be higher than the actual frequency put out by the source. And if somehow the relative distance increases between the two, the observer and the source, then the observed frequency by the observer will be lower than the actual frequency put out by the source. That's for intuition purposes. The Doppler effect is a phenomenon common to all harmonic waves. It's most familiar to us on Earth due to sound waves, but it's also true for light. Sound waves would cause a observed pitch difference. Light would cause a red or blue shift in the spectrum of what you're seeing. Let me kind of explain this using sound. Let's say a sound wave was coming in my direction. Let's say the source was stationary and I was stationary. So the sound wave is coming in with these wave fronts at a definite number per time, a definite frequency. And I'm listening to the sound as it's coming in with this definite frequency. Let's say as this is coming in, I decide that I'm going to start moving away from this source. So as I'm moving away, this frequency that did hit me here and the next one's coming in, but I start moving away, so it takes a little bit longer for the next one to get to me. And then I continue to move away, so the next wavefront that hit there takes a little bit longer to get to me after that. In essence, by me moving away from the source, I'm going to reduce the frequency of those wavefronts that I'm receiving. And hence, if it were sound, the pitch would go down because the frequency would go down. The source hasn't changed its frequency, it's just the way that I'm observing it because I'm moving. The same thing would happen if the source was moving towards me. The effective wavelength of the source would be shortened, and that would increase the frequency. Or if I were moving towards the source, that would increase the frequency because I'd receive them faster, more per second. And so the effect is that I observe something different from what is being put out. And if I can use that effect, I can figure out how fast I'm moving or how fast the source is moving, or both. Here's a Doppler shift in terms of light for a source that is moving towards an observer. And in fact, the wavelength is shortened. The speed of light is the same, so the frequency goes up, and hence it is blue shifted. It's shifted towards the higher frequencies. We call that a blue shift. If the frequency is shifted to lower frequencies, we call that a red shift. So if an object is receding, then we will observe a lower frequency, a longer wavelength, a red shift. So receding goes with red shift. And if an object is blazing toward you, then you would see a blue shift. So I try to use words that would help you remember this. Receding, red, blazing toward, blue. Here's a Doppler pattern of a tornado taken near my hometown up in Minnesota. And if you think about a tornado, it's spinning around counterclockwise. 99% of them in the United States are counterclockwise. So it's spinning around like this. So as you're looking at a tornado, part of it is moving away from you, and the other half of it is moving towards you as it's spinning around. So you got this half moving towards you, this half moving away. As you look at this signature here, the colors, actually the green is actually moving away from you and the red is moving toward you, at least in this color scheme for this Doppler radar. And so this is a pretty big tornado here, as we're seeing it spinning around over this area, and we see the differences in the wind, and that's how the Doppler radar could determine that the tornado exists there. If we were using Doppler shift on light, and hence for a star, we would see the light red shifted. In other words, the whole spectrum of whatever we're looking at would be shifted towards the red part of the spectrum. And if the star were blazing toward us, it would be blue shifted. For instance, down below here you see the characteristic spectrum of hydrogen at rest in the laboratory. But if you're looking at hydrogen in a star that was red shifted, that was moving away from us, then the whole spectrum itself would be shifted in frequency to the red part of the spectrum. We could also determine the speed of that object. You don't need to know this in particular, but just for extra information, if we could figure out the change in wavelength that was shifted, that divided by the rest wavelength for that particular frequency times the speed of sound, that ratio is the speed of the star. As we look out in the universe, most of the stars, 99% of the stars that we see out there in our sky are being redshifted. That means they're moving away from us, indicating an expanding universe. Some stars are moving toward us. And if you look at the constellation Lyra, it is actually moving toward us, and those stars would be blue shifted, or the Andromeda galaxy is actually moving toward us. But most of the stars out there are moving away from us. So here's an information summary on light. We know that we can determine the temperature of an object by its black-body curve, and incidentally you only need 2 points on that black-body curve to determine the whole curve. It's almost like 2 points on a line determining a line, or 2 points on a black-body curve determining a black-body curve. So you just need 2 filters. Look out there, determine those 2 points, draw your black-body curve. The maximum of that curve by Wien's law will tell us the temperature of the object. From the temperature, you can use Stefan's law, and the energy would be determined by the temperature to the 4th power. So you can figure out how energetic, how luminous that body is from the temperature. Then you can do a spectral analysis. You can find the composition of that light by identifying the elements that are within that light using the line spectra. You could determine the speed, at least either toward or away from you, by the Doppler shift. Radially, that'd be radially, but transverse, you wouldn't be able to do that. So you'd have to use some other technique to determine the transverse or perpendicular speed. But you could determine at least in radial direction by the Doppler shift whether something's moving toward you or away from you. You could determine the direction toward or away by whether it was red or blue shifted. You could determine the rotation rate of something by the broadening of the spectral lines due to the Doppler shift. You can determine the pressure, say within a star, by the width of the spectral lines. We didn't talk about that, but that's extra information. And you can determine the magnetic field, say of a star, by the splitting of the spectral lines. If you were to look at sunspots, you would see definite lines, but they would be split due to the fact that you have two magnetic fields present there. And so that splits by the Zeeman effect. And so by the magnitude of that splitting, you could determine the magnitude of the magnetic field. So all these things is information that you can garner from light in general. Here's an extra slide that didn't make the cut. So one that I threw out. X-rays were also discovered by accident in 1895 by Wilhelm Roentgen. Here's Wilhelm Roentgen, and he discovered X-rays. You can see why I threw this slide out. So that concludes Chapter 2, the study of light.